Thank you. So, hello everyone. I'm Gengliang, a software engineer at Databricks. I'm also a committer of Apache Spark. My major interest is on Spark code, especially on the file connectors. This talk is to show some internals about Spark viewing file sources. The first part is the Spark viewing file formats. I will introduce them one by one. The second part is the data layout, including partitioning and bucketing. At last, I will put everything together and explain the internals about file reader and writers by examples. Spark processes, integrates, and analyzes the data from diverse data sources, including Kafka, Oracle, Data Lake, and so on. Spark supports columnar formats, including Parquet and ORC. It also supports row-based formats, including Avro, JSON, CSV, text, and binary. So what is the difference between columnar formats and row-based formats, and how to choose between them? Here is an example. The table music has 4 columns: artist, genre, year, and album. Just as their names, in columnar format, data is stored sequentially by column, and in row formats, data is stored sequentially by row. For columnar format, Spark reads less data by only reading the required columns. In this example, only the columns artist and album are read. This is super useful for queries that only require a small subset of a wide table with many columns. For row-based format, the write performance is better since the write is sequential and the appending is faster. It's also useful for queries that most of the columns are required. Here is a general conclusion for choosing columnar format and row-based format. Column format is smart and optimized for big data. It supports efficient data skipping by column pruning and row group skipping, which I will explain later. It is a good choice for read-heavy workloads. If the workload is write-heavy, such as event-label data, the row-based format is a better choice. Next, I will introduce the file formats one by one, starting from the columnar format. From the top level, a Parquet file consists of one or more row groups. At the end of a Parquet file, there is a footer containing the metadata for each row group. The metadata of a row group contains the minimal and max value of each column, which can be used for filtering row groups on reading. A row group contains exactly one column trunk for each column. A column trunk consists a list of data pages and an optional dictionary page, which can be used to store all the distinct values of one column. With the information in the footer status and the dictionary pages, when predicates are put down, Parquet reader can filter row groups that are not possible to satisfy the predicate, so that it can read less data. The next one is ORC. ORC contains a list of strings. It also has a file footer, contains the aggregation information of the whole file. And inside a stripe, it contains a list of index and raw data. One index data includes max and minimal value for each column, and the row position within each column, so similar to Parquet, which such file structure, ORC can support stripe skipping as well. Now we have know the structure of Parquet and ORC and how these formats are optimized for reading. In the next, I will introduce the viewing row-based formats. So Avro is compare and fast serialization format. Avro features robust support for schema evolution by managing adding fields, missing fields, and fields that have changed its properties. With the Avro's capacity to manage schema evolution, it's possible to update components independently with low risk of incompatibility. The write performance of JSON and CSV is excellent, but the read performance is relatively slow. JSON and CSV are semi-structured, and the file itself doesn't describe the actual schema of itself. Spark provides schema inference for JSON and CSV, but it's sampling based, and it may not be accurate. The schema of JSON data source can be map or struct. By default, Spark infer it as struct, but if you decide to stick with a map, you can pass the user-specified schema to Spark. Avro and JSON has many things in common. For example, they are both row-based formats, and they support nested schema. But there are many differences as well. With binary encoding, Avro is compare and fast. It doesn't have to repeat everything within every single record. The schema inference of Avro is accurate. It is a good choice for organizational scale development. For example, there is a big team building an online product, and it requires to collect data from web, iOS, Android clients. To guarantee the data quality from all kinds of clients, and to make sure the schema is comparable in multiple releases, Avro is a better choice in this scenario. For the initial development, JSON is a good choice because the development is super easy as well as the debugging. CSV is often used for handling legacy data providers, and it has a limited schema. It doesn't support nested data types. The schema of text file is more limited. It only supports exactly one field of string type. In Spark 3.0, we have introduced a new file data source binary. The binary file format, binary data source reads binary files and convert each file into a single record that contains the raw content and the metadata of the file. The schema is fixed. It includes the file path, the modification time, and the file length, and the raw content. The usage of binary file sources is the same as other viewing file formats. You can use stock format binary file for reading, and there are two new options for all the file sources in Spark 3.0. The first one is pass global filter. It accepts a regular expression for filtering file names. The second one is recursive file lookup. By enabling it, Spark will ignore partition discovering and read all the files recursively. After introducing all the file formats, the next section is data layout, which is very important for performance tuning. The first part is partitioning. With partitioning, we can have cross-scan data skipping. The data layout looks like this way. For each partition column, there will be a directory for each partition value. Here is an example of the data skipping by selecting the year as 2009 and the genre as folk. We can avoid unnecessary data reading and partition discovery. This is especially valuable for AWS S3. There is a benchmark from our blog post, which partition pruning, the runtime of the query are reduced. Please check the blog post for more details. In SQL, we can use the keyword partition by with partition columns, and Spark will write data into partition the files. It's also supported in data frame API. The partitioning information will also be persisted in the meta store. In Spark 3.0, there is an important feature, dynamic partition pruning. The main idea is that if two tables are joined with their partition keys, we can propagate the partition value from one side to another to further filter the partitions before the join execution. Please check the talk from Borden and Ulrich in this afternoon at the summit. Well, in practice, we should also avoid creating too many partitions. Otherwise, it will stress the metastore and file system. The general suggestion is to avoid using too many partition columns and avoid using partition columns with too many distinct values. You can also try data lake. Its partition management is very scalable. Delta maintains the latest table status with transaction log. Whenever you add a file or remove a file, it will be written into logs. And every 10 commits, a checkpoint file will be computed. So when reading files, the transaction log are analyzed by Spark in parallel to get all the input files and do the partition pruning. Everything is in the log, so no need to access Hive metastore for getting the partition values, and no need to stress the file system for listing the files. With such architecture, Delta Lake is able to handle billions of partitions and files. The next part is about bucketing. If two tables are joined and the join key are of different distribution, then Spark will always perform shuffling and sorting on the join key before the execution of sort mode join. And shuffle can be very slow, especially on AWS S3. And improvement can be pre-shuffle and pre-sort with the join keys for both tables. So that when joining tables next time, the shuffle and sorting are avoided. This is very useful for tables which are frequently joined with the same key. In SQL, we can use the keyword cluster by and sort by with the bucketing columns, and Spark will write data into bucket files. It is also supported in data frame API, and the bucketing information will be persist in the Hive metastore. Usually, there is a per bucket sorting when writing files into buckets. If with columnar format, the sorted column will be searched more efficiently because of the minimal and maximal value status. So now I have introduced all the built-in file format and the data layout. I will put it together and show the internal of file reader. Here is a simple query example. Spark reads all the timestamp which happened in the Amsterdam this year. To achieve the goal, first of all, we need to understand the data so that we can read as Spark for low format. Also, we need to skip unneeded data to make the execution smarter and faster. Here is the example input data layout. Data are partitioned by the column year. In each folder, there are multiple Parquet files. Each file contains multiple row groups. Inside a row group, there are many column trunks. We notice that the query only needs the data of this year, so we can skip the data of the past 3 years. Even more, as there are metadata for each row group, we can perform row group skipping. If Parquet directory filtering, dictionary filtering is enabled, the value set of the column city will be in the metadata, so we can skip the row groups which doesn't contain Amsterdam in the column city. So far, we are doing well, but we can make it even much better. As there are many column chunks, we don't need to read them all into Spark. All we need are 2 columns, city and timestamp. Now we know how to read the data in the way of single thread. But to make the execution in parallel, files should be split into partitions. The basic idea is to treat all the files as a whole and split into partitions of the same size. First of all, driver will create partitions of equal size. And for each partition, Spark will launch read task. And then do the actual data reading. Parquet file records will be converted to Spark low format distributedly. The final part is about the file writers. Here is the last query example. We already know how to read the Parquet file as Spark low. Now we need to figure out how they are written in parallel to other files. The goal is simple. We need to make it parallel, and we want to make it as transactional as possible. We don't want any partial results in the file system if the job or task failed. Upon the write action, Spark will launch write task for each file partition. And Executor starts to execute the write task. Each task writes to different temporary paths. Before the write job is committed, everything should be temporary. And there can be multiple jobs running to write to the same path. So we need another directory level with the job ID. Task output files should also be temporary before they are committed. And files should be isolated between tasks. So there is another level of task with task ID. If a task success, it will be committed. We can see that the output of the committed tasks are moved under the directory of the job ID, and the task in progress remains temporary. Here is what happened when a task aborts. The executor will delete the path of the aborted task and let the driver know the failure. We can see that the aborted output is removed, while the committed one remains there. After Spark is always aware of the failure, Spark driver will relaunch the task, which will create a new temporary directory. After all tasks are completed, driver will commit the job. This is the final data layout. All Parquet files will be moved under the result path. In brief, Spark stages and the output files to a temporary location. If task fail, the temporary output will be removed. And if success, it will move to an upper level directory. This is almost transactional. When moving data to the final location, there can be reaccess and get partial result. For HDFS, moving files is very fast, so the window of the failure is small. But for the cloud storage, moving files are relatively slow, so the window of the failure is larger. There are solutions for this. You can check Eric Liang's talk about how Databricks DBIO resolved the problem. You can also try Data Lake because it supports for ACID with transaction log. As a summary, this talk has show all the building file formats and introduce the data layout, partitioning, and bucketing. Also show the internal about file reader and writer by examples. Thank you.
Okay, cool. Thank you very much for that. That was a superb session. I think we've got a bit of time for some questions, and we've got a couple of microphones lined up. So if you'd like to go any deeper, then just come up and ask away.
Hi, can you hear me? Yeah, my name is Ramesh. Specific question on the data loader, basically. The specific question is about when we are loading a larger volume of data, there's definitely a potential chance of one corrupt record or at least one corrupt file in the module path which you say when you try to load it with Spark. So if you actually look at it, there's this concept of dead letter path or dead letter queue in when we try to do stream processing. Is there something like that which is upcoming in the Spark file loaders for handling corrupt records or corrupt files when trying to read from a file path?
Excuse me, can you repeat the question? Sorry.
Yeah, so basically when you're trying to load a set of files from a file path, there can be one or two files which are corrupt, right? Today, your entire file load will fail because of one corrupt file in that file path, right? So
your question is that if there are some failure in the file loading, right?
Yeah, so today the file loading will fail if there is even a single corrupt file in the file path. My question is, do we have an option to skip that file while loading?
Yes.
Yeah.
There is an option for all the file source. I think it's like Spark ignore corrupt file or something. Yeah, but by default it's disabled. You can turn it on.
Okay.
Yeah.
The next is about, so the next question I had is about the commits which we are trying to do. So if you can go back to the commit stages. Yeah, so the next.
Which one?
Yeah, this one, yeah.
Okay.
So here I see that when we have job ID and then task attempt ID, only when the task completes, the file is moved from the temporary directory to the actual task ID. So one specific thing which we've seen with Parquet write mode with dynamic partition, dynamic overwrite enabled, is that the attempt ID is not accounted for in the file names. So what happens is when there is not a clean failure from the executor, if you go back. Yeah, so here you're seeing that the executor is calling an abort task. This is basically a clean failure by an executor saying that I'm aborting a task. But there are chances where an executor is removed from the Spark by Yarn for Spark for speculative resource management. So in those cases, the attempt when the attempt ID is not taken into consideration, the file basically already exists there.
But even if it happens, it's under the temporary directory with the failed task attempt ID, it won't come out to the result folder.
Yeah, so I agree. So my question is this task attempt ID consistent across all type of Parquet modes of operation? Because Parquet mode has overwrite as well as append. So is it consistent across all modes of Parquet, right?
Yeah.
Because I specifically seen in the overwrite mode of Parquet that the task attempt is not being used in the file name. And that's why I'm trying to.
Not very sure about the question, but I think everything should be temporary, and only the committed tasks are moved under the job, and for override I think it's the same. No much difference. Right?
Okay, I can connect back with you.
Okay. Yeah.
Hi. So in your example of reading JPEGs, could you compare the recursive scan with partition discovery? How they differ?
Which example? Like reading?
The dataset of JPEGs. There was an option of
stripe?
Yeah, the binary files of recursive scan. And you were saying that you're ignoring partition discovery. Can you just compare the two approaches?
Wait, the recursive one, right?
I think it was somewhere in the beginning.
Yes, in the binary file, right? Yeah. So yes, so the target file can have many subdirectory, like a lot of level, and by default, Spark will perform partition discovery. The directory that it will try if it's partition. Otherwise, it will just read the files under the folder without going deeply into the subdirectory. So if with this new option, recursive file lookup, it will read all the file. Just like we are executing the find command in the Unix or Linux. Okay.
So the recursive lookup is done on the master as a single task, sort of?
Single task.
So is the recursive lookup done on the Spark master?
Yes, sure.
And it's not done on a Spark job?
Yeah, so for before the actual reading, the driver will look up all the files and do the partition pruning, including recursive lookup all the files, and then it will know the total information of which files we should need, and then and then it will divide them into partitions with the same size, and then distribute the task.
Okay, but how does this differ from partition discovery done on the Spark master with a single task?
Pardon?
How is this different to partition discovery done on the Spark master with a single task?
Because sometimes the scenario is that we don't want this partition discovery. The folder is no partition at all. It has many weird level like dogs, cats, the pictures, something like that. So we can directly go through and there's no partition. Yeah.
Okay, and just last question. So I've played with partitioning a bit, and it seems that just passing the base file path to when loading a dataset seems to work a lot faster than actually passing, if for some reason you know all the Parquet files in the directory that's partitioned, passing them all at the same time. When you load the dataset, this seems to work a lot slower. Do you have any idea why?
Well, I think it's the time cost in the file listing. No, so you mean that?
Yeah, I actually mean the opposite. When you already know all the Parquet files in the partition directory and you pass them to the load, it seems to work a lot slower than actually only passing the base file path.
Oh, then I'm not sure of that. I think if you know all the files and they are no directory, I don't think they are slower, because you don't need to like do the file listing. I'm not sure.
It makes total sense, but just in my experience, it's the opposite.
Okay.
I was just wondering if you have any clues on why.
Yeah, maybe I will look into the issue. I will try myself. Okay, thank you.
Hi, thank you very much for the presentation. And so my question is, suppose we have a good partitioning of our data in HDFS, and if we work with Yarn, for example, and we want to read the data, is Yarn capable of choosing an executor that will be in the same worker node of HDFS to read the partition from the same executor without having to shuffle the data across workers?
Oh, so your question is that is it possible to always use the same ejector to read the same partitioning files? To read all the files under one partition, right?
No, actually, if we partition our data, and suppose we have one partition in a worker node 1, and if we want to read the data, I have a select to filter only on this partition. Is Yarn capable of placing the executor on the same worker node to read the data, to have a local locality of data, or it will just give you an executor across your cluster and then shuffle the data from the worker node of Hadoop to your Spark worker?
Sorry, I don't understand the question. My English. Okay.
So I think the question is around will Yarn spawn an executor locally to where the data resides?
Yes.
Is that right?
Yes.
Okay, and we're talking about like on-prem Hadoop or something like that in this scenario?
Yeah.
Okay.
Or even with the S3.
Okay. So I mean maybe this isn't a canonical answer, but I mean the data will be distributed around the cluster and replicated. So it doesn't reside in on just one node. Does that make sense?
Normally, if we partition the data and then I have a small partition, it will be on a specific node. So is Yarn capable of telling the Spark executor to be in the same node or no?
But the data would be blocked up and distributed to other nodes, right?
Yeah.
Right. So the data wouldn't live just in one directory on one node. It would be scattered around the cluster. Does that make sense? Or have I missed something?
Yeah. It does. It makes sense. But if we filter to read only this partition,
Yes.
It doesn't make sense to have an executor on another worker, not the same one that contains the data.
Yes, so I understand that you'd be pushing down just to one partition in one folder.
Yeah.
But I think the data in that partition would still be replicated and scattered to many different nodes.
Okay.
But with regard to your question about how Yarn allocates executors based on the locality,
yes.
I'm not sure. Do you have any insight around that?
No.
Okay. All right.
Okay. Thank you very much.
All right.
Yeah, thank you.
Hi.
Hi.
At the beginning of the presentation, you said raw format is better for streaming data, coming really fast and write a lot.
You mean the low columnar format and low base format, right? Do you mean
Yes.
Yes.
This one. Yesterday and today we talk about Delta Lake a lot. That is basically Parquet files plus transactional logs.
Yes.
So it's a columnar format. And,
yes.
From your perspective, which is the threshold, whether to choose this approach or which one is the threshold that you must use the raw format because the file is coming too fast and you can't use the other format? If there is a threshold about the number of writing per second or stuff like that.
So I think the question is around how does the velocity or the frequency of the data coming in steer your choice of file format? Is that right?
Yeah.
Okay.
So how to decide whether it's really heavy workload or light heavy workload, right? I think it's quite natural, but because if the data is like you have a lot of data coming from streaming or batch, and I think you can, one way is that you can count the times, how many times you read the data and how many times you write into the data. If you are analyzing the data a lot, then it's really heavy. If it's mostly for collecting the data and you need to ensure the system and the data pipeline is robust, then you should try the low format, and maybe when analyzed, you can convert it into a columnar format. Okay.
It's also probably just worth mentioning, like the formats aren't mutually exclusive. Like it's quite a common design pattern to have, ingestion in, raw or human readable like JSON or Avro, and then have a job convert that to something like ORC or Parquet or Delta, and have effectively the same data in a couple of different formats. So they're not really mutually exclusive.
Yeah, and also this is not the only consideration. If you have you need the schema evolution, you should also consider Avro. It has the best support among all the building file sources. Like Parquet only support adding and removing columns, so does ORC. But Avro support like default value for the columns and documents, and you can even rename the column. So it has more features.
Good. Well, guys, thank you all very much for coming along today, and thank you as well for doing the talk. That's been fantastic. I think we're about at time now. So if I could just encourage people to rate the sessions as they go along, as they go around today, then that's really important for our feedback. But yeah, thank you guys all very much for coming along, and enjoy the rest of the sessions.